Hello everybody, this is Nageswara, Assistant Professor of Physics, Government Degree College, Chintalapudi. In this presentation, I want to analyze what is spherical aberration and its elimination methods. Before discussing about the elimination methods, you want to remember what are monochromatic aberrations, how many types of monochromatic aberrations are there, and what is spherical aberration. And thereafter, we will analyze elimination methods of spherical aberration. So, what is monochromatic aberration? So, we know the aberrations in which the object is single color, that is monochromatic light. The image is not a perfect image. The image may be distorted or blurred or find at different positions. This kind of defect in lens is called monochromatic aberrations. So we know monochromatic aberrations are five types. One is spherical aberration, second one is coma, third one is astigmatism, fourth one is curvature, and fifth one is distortion. We know spherical aberration and coma can produce blurring of images. But last three, that is astigmatism, curvature, and distortion, produces dislocation with the image. This is the main difference between spherical aberration and coma and astigmatism, curvature, and distortion. So, what is spherical aberration? In this spherical aberration, the object is placed on the principal axis of the lens. So, where this is the lens EL, this is the principal axis, and a point object O is placed on the principal axis. Then paraxial rays formed an image at IP and marginal rays formed an image at IM. So the distance between IM and IP is measurement of spherical aberration. So the failure of the lens to form a point image of an axial point object is called a spherical aberration. So how many methods are there to minimize the spherical aberration? There is different methods we have to minimize the spherical aberration, in which by using stops, by using plano-convex lens, by using two lenses are in contact, by using crossed lens, by using two plano-convex lenses separated by a distance, and the last one is by using a planatic surface. By using these six methods, we can eliminate the spherical aberration. The first one is how to use steps. We can minimize the spherical aberration. So we know the spherical aberration due to the different focal lengths of different zones. In any convex lens that is divided into different circular zones, we know the spherical aberration is varied with the focal length of the lens is varied with the radius of the each circular zone. Due to this focal length changes, the marginal image and the paraxial image are at fair distance. This kind of defect is called spherical aberration. So by using proper stop in front of the convex lens, we can minimize the spherical aberration. So this is the convex lens, and this is the slit in front of the convex lens. If rays are incident on the slit and lens from the infinite distance, the marginal rays are blocked by the slit, and paraxial rays are incident on the convex lens and formed an image at I. So in which the only paraxial image is exist on the principal axis and marginal rays are blocked at the slit. So that by using this stop we can minimize the spherical aberration. But there is some defect by using this stop so to minimize the spherical aberration, because the image intensity is very much reduced by using the stop. And the second one is by using plano convex lens or by dividing the deviation equally. How can we? In which the plano convex lens may be used to minimize the spherical aberration. So before discussing this elaborately, we have to take a convex lens. So this is the principal axis. A point object is based on the principal axis. Then the ray is incident on the convex lens and the image is formed at the other side of the convex lens. Then the incident ray makes an angle delta 1. This is called deviation, and the delta 2 is the refracted deviation. So if there is deviations delta 1 and delta 2 are equal, the spherical aberration minimizes. According to this theory, the spherical aberration is depending on the total deviation by the lens. So the spherical aberration is directly proportional to delta square. Well, delta is the total deviation by the lens at the two curved surfaces. So there is delta 1 and delta 2 are the two deviations, so that delta is equal to delta 1 plus delta 2 is the total deviation. So the spherical aberration is directly proportional to delta 1 plus delta 2 whole square. We know a plus b whole square is equal to a minus b whole square minus 4ab. According to that, spherical aberration is directly proportional to delta 1 minus delta 2 whole square plus 4 delta 1 delta 2. If delta 1 is equal to delta 2, then the spherical aberration is directly proportional to only 4 delta 1 delta 2. So if delta 1 is equal to delta 2, it means the deviation is divided equally at two surfaces. The resultant deviation is minimum, and hence the spherical aberration is also minimum, in which case the spherical aberration is equal to 4 delta 1 delta 2. So the condition for minimizing the spherical aberration is delta 1 is equal to delta 2. So in this diagram figure A, the curved surface is towards the object. The rays is incident on the curved surface and refracted and incident on the plane surface. So up to now there is one refraction at the curved surface. When these rays incident on the plane surface again refracted at a plane surface and images formed at Fm and Fp. So in which there is two refractions, of one and the second one. One is refraction is curved surface and the second refraction is at plane surface. So there is a two deviations in the figure A. In case of figure B, there the plane surface is towards the object. So the rays coming from the infinite object is incident on the plano-convex lens and does not deviate at the plane surface, but deviated at the curved surface and images formed at Fm and Fp. So in case of figure A, there is two deviations, but in case of second figure B, there is one deviation. So in case of two figure A, the deviations are nearly equal, so the spherical aberration is minimum. In case of figure B, the deviation is maximum, so that the spherical aberration is also high. So the spherical aberration is minimum in first case and maximum at second case. The general rule to minimize the spherical aberration in a plano-convex lens is that the convex side should be face the incident or emerging beam, whichever is more parallel to the axis. So in this first case, these parallel rays are towards the curved surface. So figure A is best suited to minimize the spherical aberration. And third case, how can we minimize the spherical aberration? By using a suitable lens in contact. So we know in case of a convex lens, the marginal image is towards the left of the paraxial image. But in case of a concave lens, the marginal image IM is right side of the paraxial image. So if the spherical aberration is positive in case of the convex lens, the spherical aberration is minus in case of the concave lens. So the combination of the convex lens and concave lens can minimize the spherical aberration. So it has been observed that in case of a convex lens, the marginal rays image IM lies towards the left of the paraxial image, while in case of concave lens, the marginal image IM lies towards right of the paraxial image IP. So this suitable combination of two lenses minimize the spherical aberration. And fourth case is by using the crossed lens. What is crossed lens? Crossed lens is also one of the lens. It is prepared specially by following the formula R1 by R2 is equal to 2 mu square minus mu minus 4 by mu into 2 mu plus 1, where R1 and R2 are the radius of curvature of convex lens or plane any lens, and mu is the refractive index of the material. If in case of refractive index mu is equal to 1.5, from the above equation, R1 by R2 is equal to minus 1 by 6. When any lens is preparing with this formula, that is R1 by R2 is equal to minus 1 by 6, will minimize the spherical aberration. If it is 1 is taken as plus 1, that is convex lens, it is minus 6, that is the concave lens. If convex lens and concave lens are convex shape and concave shape prepared in the same lens, by taking this formula R1 by R2 is equal to minus 1 by 6 can minimize the spherical aberration. If refractive index mu is equal to 1.66, in this case R1 by R2 is equal to minus 1 by 6.5. The lens prepared by this formula is also can minimize the spherical aberration. And if the refractive index mu is equal to 1.686, then R1 by R2 is equal to 0. It means that this is plano lens. This plano convex lens, by taking this R1 by R2 is equal to 0, this also can minimize the spherical aberration. So the lens satisfying the above condition can minimize the spherical aberration. This is the fourth case. And fifth case is by using two plano convex lens separated at a distance. This also will minimize the spherical aberration, where there is two lenses L1 and L2 placed at a distance of d. The focal length of the convex lens L1 is taken as f1, whose focal point is f1, and focal length of the second convex lens is f2, whose focal length is f2, that is f2. Now, when the object is at an infinite distance, the rays came from the object is parallel and incident on the convex lens L1 on the curved surface. We know at the curved surface, the ray is deviated along the direction of BC and incident on the curved surface of the lens L2. L2. Now there is delta 1 is the angle of deviation at the curved surface L1. This ray is again deviated along CF2, and this ray making angle delta 2 is deviation at the second curved surface. The total deviation delta is equal to delta 1 plus delta 2. We know when delta 1 is equal to delta 2 is the condition to minimize the spherical aberration. Now, where L1 and L2 are two plano convex lenses having focal length f1 and f2, place at a distance of d. Let a ray AB is parallel to the x-axis incident on the lens L1 here, where delta 1 is the angle of deviation that is equal to h1 by f1. Wait, how it is h1 by f1? Where delta 1 is the deviation angle that is equal to tan theta is opposite by adjacent, that is h1 by f1, where h1 is the height of the image which is incident on the convex lens L1, and f1 is the focal length of the convex lens L1, that is tan theta is really equal to theta that is opposite by adjacent. We know delta 2 is the this angle deviation angle at second lens. According to that, delta 2 is equal to h2 by f2. So delta 2 is equal to h2 by f2. We know the condition for minimization of spherical aberration is delta 1 is equal to delta 2, that is h1 by f1 is equal to h2 by 2 h2 by f2. So that the h1 by f1 is equal to h2 by f2 for minimize the spherical aberration. So that h1 by h2 is equal to f1 by f2. When there is two triangles we have from the triangle BL1 F1 BL1 F1 and CL2 F2 F1, these two are uh, equilateral triangles. From that H1 by H2 is equal to L2 F1 by L1 F1 by L2 F2. But we know L1 F1 is equal to focal length F1 and L2 F1 is equal to, that is L1 F1 minus L1 L2. So that H1 by H2 is equal to F1 by L1 F1 minus L1 L2. We know L1 F1 is equal to F1 focal length of the first lens, and L1 L2 is equal to small d, that is distance between two lenses. So that H1 by H2 is equal to F1 by F1 minus d. So we know from this equation H1 by H2 is equal to F1 by F2, and from this equation H1 by H2 is equal to F1 minus by F1 minus d. So that F1 by F2 is equal to F1 by F1 minus d. So when we substitute to this equation, F1 by F2 is equal to F1 by F1 minus d, where F1 is cancelled each other, so that F2 is equal to F1 minus d. From this, d is equal to F1 minus F2. So this is the condition to minimize the spherical aberration by using the two plano convex lenses. If two plano convex lenses placed at a distance of d that is equal to difference of the two focal lengths will minimize the spherical aberration. So these are the different methods to minimize the spherical aberration. Thank you.